Alright, so you've probably heard me use the term specify, like specification or specify this, specify that. That term gets used a lot in SEM models to refer to the act of translating or creating your model and actually figuring out what predicts what and all that stuff. So the process of deciding what variables go together, what predicts what variables are indicating factors, that's all part of sort of model specification. And then once you have a model specified, you need to figure out if the model is identified. So identified, it literally means, can we actually estimate it, or are we gonna, we're gonna run into errors? Because there's so many unknowns and so many different equations going on at the same time, the only way we're really gonna be able to know if we can estimate everything is that we have to follow some rules to make sure there are some things that in the models that are fixed, some that are free, but not everything can be free. We can't estimate everything because there's not enough information to do that. So we have to have some information about what is going to be fixed, like what are going to be zeros, what are going to be ones, so that we can actually estimate then the free things. And we have to make decisions about how to do that. And that's sort of the identification part. And then once a model has been specified, we know it's identified, then it can be estimated. So that's that process. Specification, identification, estimation. And then we're not really going to go into a whole lot about the estimation process. We're going to leave that to the sort of black box, behind the scenes sort of thing. But we do need to make sure that when we specify a model, that it can be identified so that it can be estimated, or else we're going to get all kinds of funky errors that are not going to be good. So model specification is the process of converting a theoretical model. Like you have hypotheses and stuff that you want to test. So how do we actually convert that and put it into a model? Into equations with coefficients that can be estimated. Specification is a drastically important first step, as it requires that model be translated correctly and reflect your variables accurately. All right, so whether you're doing a path analysis or some kind of full SEM model, we have to be able to translate those models over and make sure that they're actually accurate, reflecting what it is you really want to test, and then also that they're identified. So model identification is probably the most important step. That when you're doing model specification, you need to make sure that things are identified. Only identified models can be estimated. So that's the trick. The key here is that model identification, only those that are identified can be estimated. So we have to make sure that models are identified. A model is said to be identified. There's actually lots of rules, okay? But in general, if there is a unique solution for every estimate. So if y equals 10, and 10 is the only sort of way of thing you can estimate for that, then great, that's identified. When you have y equals a plus b, well, in order to do that, you have to be able to decide which one of those you want to actually estimate. I can estimate either a or b, but I can't estimate both because I have to fix one, estimate the other. But I can't do both simultaneously, or there's essentially a infinite number of solutions that can actually go into that. So the bottom line is some parts of the model need to be fixed in order for the model to be identified, and that way we can actually estimate those that are free. This is especially true for sort of complex models. All right, so the more complex a model becomes, the more you really have to be sure that everything is identified and you're sort of following all the rules to make sure that things are identified. So step 0. Right? So this is really like a pre-step to model identification. So that you have to remember that we're not analyzing the raw data, right? So the data gets converted to a variance-covariance matrix, and then that's what we end up actually, analyzing. So the data are components in either the variance-covariance matrix or correlation matrix, depending on which way how you're actually estimating them. And we count the number of data points available by looking at the unique elements in a variance-covariance matrix. So the numbers down the diagonal and either above or below the diagonal, but not both. So what the hell am I talking about? So when you think about variance covariance matrix, right, you have, say, this one now, like y1, y2, y3, and y4. And we're going to then also have y1, y2, y3, and y4. All right, so we have 4 variables that we're trying to model. This is going to be a really small, very simple model. down the diagonal of this are the variances. All right, so this is the variance of, let's say it's 1 with 1. This is the variance of 2 with 2. Let's maybe line it up right. Variance of 3 with itself. And then the variance of 4 with itself. All right. Then the off diagonal are going to be the covariances. This is the covariance of 2 with 1, covariance of 3 with 1, covariance of 4 with 1, covariance of 3 with 2, covariance of 4 with 2, and then the covariance of 4 with 3. All of those are going to just repeat. So when you see it state here, right, we count the number of data points available by looking at the unique elements in a variance-covariance matrix. The numbers down the diagonal and either above or below, but not both. All right, make sense? Because once you take into account the off diagonal of one side here, the other side then is not unique anymore. So with 4 variables, how many unique items do we have? We have 1, 2, 3, 4, plus 1, 2, 3, 4, 5, 6. So with 4 variables, there are 10, ends up being 10 unique elements. That is the size of our data set. All right? Our data set is essentially 10 elements large. All right? There are 10 things that need to be accounted for in this model. I don't want to necessarily have to do this all the time, like to write this out and count up, especially as the number of items gets larger and larger. So there's a way to sort of figure this out and count the number of elements that you have before you even get started, so you know how many things you're trying to estimate. And the goal is, if I have 10 unique elements in a variance-covariance matrix, I don't want to explain them with 10 different parameters. I want to explain them with something substantially smaller. Usually the goal is data reduction. I want to actually reduce the amount of things I'm trying to estimate. So that's where it becomes tricky. How do we estimate 10 things with less than 10 things and still have a model that is identified? Right? That's sort of the goal of all this process. So the unique elements in a variance-covariance matrix are the values in the diagonal plus the one side of the off diagonal. You can solve for the number of these elements using this equation. So the first part of this blurb is just a repeat from the previous slide, but it's basically the unique elements are the variances, and then you count 1/2 of the covariances, because the covariances just repeat. Instead of having to set up a matrix and count the number of elements, we can instead use this equation, which it will give you the number. It's like a simplified version of a permutations equation that looks at how many, if you have p numbers of items, how many of those can you take 2 at a time, essentially. So this is p is the number of items, number of variables. So like, for instance, in that last example, if we have 4, all right, so 4, if p is 4 times 5 divided by 2 is 20. Divided by 2 equals 10. So we can actually estimate the number of parameters that we actually are going to, not parameters, the number of unique elements, the number of data points we have in our model. So this gives us then a target. I have 10 things that need to be sort of accounted for in a matrix. So now I'm going to go about trying to create a model that will explain as much of those 10 items or those 10 elements as I can, hopefully with fewer parameters than 10. With me so far? So as a model is specified, as you start to specify the number of parameters that are either fixed or estimated. If it's fixed, it doesn't get counted towards the number of parameters that we're going to estimate, and cover those 10 elements. It's the number of free parameters that we're trying to. The number of free parameters can't be more than the number of unique items you have, and typically our goal is to try to get less than the number of unique elements we have. So the first step in model identification is evaluating the number of parameters relative to the number of unique elements in the covariance matrix. What the hell does that mean? In SEM, anything that's free, a free parameter, those that are going to be estimated. Those are all the asterisks we were just talking about in that last model. So we got to count the number of asterisks, the number of things we're estimating, and make sure that we have enough degrees of freedom, the difference between our data, the variance covariance matrix, and the number of parameters we're estimating. We actually want there to be some degrees of freedom there. You can estimate a model that has 0 degrees of freedom, meaning that you're estimating 10 things with 10 parameters. It's sort of boring, but you can do that. You just can't estimate more parameters than you have data points. Then you start getting to negative degrees of freedom, which obviously is not good. And if you want to test for model fit and other things, then you have to have some degrees of freedom to do that. So there are 3 forms. This is just referring to the number of parameters versus number of unique data points. You have over-identified, just identified, and under-identified. They may sound a little bit backwards, but over-identified is actually what you want, typically. You have more data points than parameters. Or the other way of saying that is you're trying to estimate data points with less parameters. I have 10 data points, but I'm only estimating it with 8 parameters. Okay? So you're trying to reduce the amounts of parameters you have to estimate in order to cover all the variances and covariances. Then you have just identified, which means that the data points and parameters are the same. They are the same number. So this is a 0 degree of freedom model. You can't test for model adequacy or anything in model fit, but you can estimate everything. You can estimate all the parameters. It's just not very fun. You haven't done any kind of data reduction whatsoever. And then you have the worst case, which is under-identified. There are more parameters than data points. You really can't do anything. You can't estimate anything. There's not enough things that are fixed in your model to really estimate the number of free parameters you have in the model. So all you can really do is try to take something that is free to estimate and fix it so that you can actually reduce the number of parameters you're estimating and hopefully get it to be at least just identified, if not over-identified. So over-identified is the best case scenario. The minimum is just identified, and the under-identified is where you actually can't estimate the model. You're stuck. You can't do anything with it. So questions about those things. Over-identified, under. It sound like you're talking about steak or something. So overcooked, undercooked. Or like, I guess, just would sound like the perfect thing, but actually you want, in this case, to be over-identified. That's the main goal, typically. If it's a really simple model, you only have a couple things, you're doing some kind of regression, then a just identified model is fine. It's just if you actually want to look at model adequacy, like is your model really doing a good job, then you have to have some degrees of freedom, which means you have to have an over-identified model. Step 1 requires that a model be at least just identified, but over-identified models are preferred, and we're trying to explain more data with less parameters. That's sort of the goal, data reduction. I think about EFAs and just factor analysis in general. We're typically trying to reduce the number of parameters or the number of things we need to explain all the correlations, in this case, the variances and covariances. Okay. So step 2, we're going to talk about step 2 in sort of 2 different parts. You have 2A and 2B. The factors in the measurement model need to be given a scale. So I just mentioned this a second ago, but for a factor to exist, right, to have a factor, to have a thing that you're actually estimating, like remember the factors don't actually exist in real life, right? They're imaginary, they're metaphysical. We actually have to have items that are going to try to explain those things or try to the factors driving. So we actually have to bring those factors to life. We have to give them a scale. We have to make them usable. So to do that, we have to follow a couple rules, and you can go one or the other. You can either standardize the factor by setting the variance to 1. All right, so we're gonna, it's called like the unit variance approach or something like that. You can set the variance to 1, which is perfectly fine. It just means your factors are all standardized. They're all z-score metrics of some sort. Or you can decide on one of the indicators of that factor. You can set the loading of that factor to 1, and then that puts the scale of the factor, sets it equal to whatever that item is. It doesn't mean that the items are the same thing. It just means that now when you estimate the variance of the factor, you actually are getting that variance in the same metric that the item is measured in. So the factor, if the factor is exogenous, it really doesn't make a difference. You can pick either way. You can do it either way. If the factor is endogenous, most of the time, most set the factor variance to 1. Now this is coming out, I think, out of Klein's book, and I remember when I was going through this that I don't necessarily agree with this. I think it's actually the other way around. I think it's well, all right. So when you're actually going to predict, the predictor is the one that's actually going to sort of give the slope some scale. So you're interpreting the size of the loading when it's unstandardized. You're gonna be looking at sort of the predictor scale. So it makes sense in some way. But I think when you set the endogenous variables to 1, it sort of also makes it goofy. You're making that standardized. So the way I typically think about it is if you wanted to do the unit variance like this, then do that for all the factors. Keep them all on the same sort of standardized scale. If you don't want things to be standardized, then use the unit loading approach instead for all the factors, so that they're all then unstandardized, and it makes sense to sort of predict them and have them predict one another. Because if you start to switch them, some are standardized and some aren't. It seems sort of an odd way of doing it. So I would just sort of stick to either do all one way or all the other. Different programs have different defaults. EQS, the default is unit loading, meaning that it just randomly picks them. Just whatever's the first item going left to right in your data set, right? Whatever the first item is that loads on a factor, that loading gets set to 1. The only downside to that is you then don't get an estimated loading. It doesn't actually estimate an unstandardized loading for you because you're fixing it to 1, and it also doesn't test for significance. You can get a standardized loading from it, but the unstandardized version with like the test for significance won't be done because you fixed it. So a lot of times people will use the unit variance approach because they want to estimate all the factor loadings and have tests for significance for them. Depends on what you want to do. Depends on what you're interested in, what the important part of that step is. Okay, so you have to give the factors some kind of scale. You have to make them real. You got to bring them to life. You got to give them a scale in some way, either by setting the scale to a z-score standardized metric, or by making one of the loadings 1 so that it now has the same variance and same scale that that item does. Okay. The second part of this, so part 2b, for factors to be identified. There is only one factor. If there's only one factor, then you have to have at least 3 indicators. 3 indicators with non-zero loadings and no correlated errors. If there is more than one factor and 3 indicators with non-zero loadings per factor, then you want to make sure that there's no correlated errors, no complex loadings, and you can let the factors covary. All right, this is where it starts to get a little bit funky. Like, okay, well, what does all this mean and why? If you think about factors, all right, so a factor is supposed to be a collection of items that are all being driven by the factor. If you just have 2 items, you're only talking about one correlation. You're establishing a factor with just one correlation. Well, that's not really a factor, that's one correlation. When you go to 3 items, you now have 3 correlations, and you're now trying to establish that there's a pattern in those 3 correlations that make up a factor. That makes more sense. So the way I remember thinking about it was, if you think about the analogy I always thought of was like a table. Like if you have a two-legged table, it's not going to stand up very well. At bare minimum, you have to have at least 3 legs for a table to stand. So same thing goes with factors. Factors have to have at least 3 items in order to make the factors sort of work, in order for it to be a factor and not just a single correlation. Now, if you have more factors, as the number of factors start to grow, like if there's more than one factor, then it starts to, you can start to be a little more flexible. For instance, you can have a 2-item factor, which again is just based on one correlation, but you can have one as long as that factor correlates with another factor. So again, think about the table analogy. If I have two-legged tables, they could stand if maybe you sort of attach them together. Right? So as long as they're sort of attached to one another, then it's likely you might be able to identify those factors and make sure that you actually can estimate the model. All right, so the take home here is the bare minimum should be that you have 3 items at least, and you want in order for the items to be clean and the factor to work, that's why it says you have to have no correlated errors. So if errors correlate, that means that items are related for reasons outside of the factor. So that means the factor is not explaining all the common variants. There's other stuff going on. So if you have one factor, you should have no correlated errors. And if you have even more factors, if they're all really small, like they only have 3 indicators, then you still shouldn't have any correlated errors, and you should have no complex loadings. And you should let the factors covary so they can sort of lean on one another and sort of make the model work. So in terms of identification for factors, there's 2 parts. You got to give the factor a scale by fixing the variance to 1 or fixing one of the item loadings to 1. And then you have to have enough items to make sure the factor can sort of stand on its own, right? To make sure that it actually can be estimated. So at least 3 indicators. There's actually more. So if there is more than one factor and a factor with only 2 indicators with non-zero loadings per factor, then you want to make sure there's no correlated errors, no complex loadings, none of the variances or covariances among factors are 0, meaning that it has to actually be correlated with some other factor in order for it to stand up. You got to be able to tie it together, and it's got to be a significant loading. It's got to be non-zero, and it's got to be able to hold up or be held up by other factors that likely have more items. So this is like the bare minimum. My factor should likely have more than 3 items for it to be a factor. Usually we think about items being 10, 12, 15, 20 items and stuff together. Step 3. Relationships among the items and factors should either be orthogonal or recursive to be identified. So now we're back to that recursive thing again. All the item predictions and things need to go in the same directions, right? Recursive models have no feedback loops. They have no correlated disturbances. They have non-recursive models contain those feedback loops and correlated disturbances or correlated errors. Non-recursive models can be identified, but they are difficult. There are some versions, some kinds of non-recursive models that you can estimate, but they're a pain in the butt, and oftentimes you can't. I mean, you're supposed to be able to, but oftentimes you get a lot of errors and it won't actually estimate anything. So you want to make sure everything's recursive, everything's moving in the same direction, you have no correlated errors for the endogenous variables. And as long as you follow those 3 steps, right? You have model specification, model identification, and model identification and all these things. You want to make sure that you have enough degrees of freedom. You actually have more data than you have parameters you're trying to estimate. You got to make sure the factors exist. You got to give them a scale. You got to make sure they have enough items to sort of stand on their own and be able to be estimated. And you want to make sure that the whole model, the structural part especially, is all sort of recursive and going in one direction and no feedback loops. Questions? Do you have any questions about this stuff? Because that's pretty much the spiel on specification, identification, and we'll talk just a second about estimation. And we're essentially covered all this stuff. I mean, we're going to see more of it as we sort of start to apply things, but this is basically it for those 2 topics. So Yeah, so the examples will come as part of the lab. We start to run stuff, we start to look at things. So we have to like wrap up the last couple of slides next time, and then we can talk about it. Because if you actually look at the syllabus, the next class in the syllabus is essentially review and then exam. That's where we are. So so I'm asking, I just realized we're coming to close to the end of this, where, you know, there's really a few more slides talking about some basics of estimation, and then that's all the topics that are going to be covered for the first exam, which is going to be a little bit odd in the sense of, especially, so for the lecture part it's fine. For the lab part, the focus is going to be mainly on some of the review stuff we did, and then the stuff we're going to talk about today, which is looking at the specification stuff of models based on list roll versus Bentler weeks. So there's not going to be a whole lot of like heavy duty like output and stuff to interpret that isn't, it's like new stuff. It's all going to be focused on making sure you understand those different model conceptualizations between list roll and Bentler weeks. But we'll talk about these last few things, just about the different ways in which these things get estimated. It's really, there's like 4 slides. We'll talk about that briefly, and then we can start reviewing. If you feel like we need more time, we might be able to push the exam, you know, maybe a day, but not very much more, to sort of talk more about this stuff and to cover more of it. But we'll see. We'll see how things go on Tuesday and see how everybody feels about the material, and we'll make that decision then, I guess. Let's stop here. So one of the things I wanted to do is to we talked about model identification, so I figured let's like review what those steps were, preferably without going back and looking at the notes yourself, just sort of trying to get at what those steps were we talked about. So we talked about specification, which is sort of a little bit what we did in lab, where you take a model and you sort of translate that into equations and stuff to figure out. And then once you sort of specify the model, there are these steps to go through to make sure that the model can be identified. So talking about identification, what are those, you know, what are those steps? What are the things we're talking about when it comes to identification? When we talked about those things, what were all those pieces to making sure that a model is identified? They were labeled in this sort of strange way. Step 0, step 1, step 2A, step 2B, step 3. Because really, step 2, they're sort of linked together, but there are 2 pieces to it. That's why I sort of separate out in 2A and 2B. Step 0 really isn't a step. It's just in order to do step 1, in order to figure step 1 out, you have to look at step 0 first. I know you guys are looking back at your notes, but I want to see how much you can remember just from talking about it last time. You're probably wondering how I can tell. It's like all of a sudden you're getting very, very intense looks on your face as you look at your screen. I'm not expecting you to know these. This is why it's a review, so I can just see what pieces do you remember? What things were required for identification? So identification, remember, has to do with, there are like basically rules where certain things have to be fixed, certain things have to be free. You know, so you have to fix certain things in a model in order to estimate other things, right? Because you can't estimate everything all at one time, because there's basically an infinite number of solutions if everything's being sort of solved for. So there's certain things that have to be sort of specified as fixed, either 0s or 1s typically, so that we can estimate the other things that we want to estimate. So the process goes, you got specification, where you're translating a model into equations and things. And then with those equations, there's then these rules about, okay, well, what things do we have to do to make sure that a model is identified? And if a model is identified, then it can be estimated. So it goes specification, identification, and then estimation. We haven't got to the estimation part yet because I figured we should probably review the identification parts first, just to make sure we're on the same page with this stuff before we go on to talking about estimation. Even though we're not going to spend a whole lot of time on estimation, but there's one part of it I at least want to show you and talk a little bit about before we move on to other stuff. So if we're translating a model over, and we're trying to make sure that that model works, that we can actually do it, that we can actually do the model the way it's supposed to be, what were those steps? You want me like, maybe I'll give you step 0 and then see if you can figure out the rest of the steps from that, maybe. So step 0 had to do with number had to do with the number of data points, figuring out how much data you actually have. All right, and that was that p times p plus 1 over 2 equation. Sound familiar? So once you figure out the number of data points, then what's step 1? So in step 1, we're going to take the number of estimated parameters minus the data, right? Number of data points. And then we have those 3 categories. Remember what those 3 categories were? So what if your estimated parameters and the number of data points you have are the same, and when you subtract them you get 0? What's that called? Yep, so we have, let's call it just identified, JI, just identified. So what if you have more data than parameters? It's actually really the other way around. It should be data minus parameters. I have it backwards. But you figure out the number of estimated parameters, and then you're going to subtract that from the data, not the other way around. So this means 0 degrees of freedom, right? So if I take my data and I subtract the number of parameters and I have a positive number, I actually have a degree of freedom. What's that called? Over-identified. All right, so that means you have positive degree of freedom. Right? It could be 1. As long as you have 1 degree of freedom, the model is considered over-identified. And even though it has the word over, which sounds like, you know, maybe bad or something, like it's too much or something, that's actually what you want. Typically, is an over-identified model, because then you can test it for fit. You actually have a degree of freedom you can use to test it, and we'll get to that later on. If you take your data points and you subtract the number of parameters, and there are actually more parameters than data, what's that called? So there's over-identified. So what's the other side? Under-identified. That means you have a negative degree of freedom, right? Which is not, actually it's not possible. You can't try to estimate more things than you have data for. It doesn't make any sense. Like, you're trying to do too many things than you have data points for. All right? So that's sort of step 1. Do you have enough data versus parameters to be able to subtract, to be able to get at least a 0? I mean, at least you want them to be the same. It's just not very interesting, right? If the number of parameters and the data are the same, you can estimate everything. It's just you've estimated 10 things with 10 things. It's not super interesting. Remember, the goal, at least the overlying sort of push with all this stuff, you're trying, the word, I'll throw this word out now just because, why not? There's a word, parsimony. You know what parsimony is? So it's like if you're writing a paper and you've ever been told, like, that you need, to write more concisely or whatever, to be able to cover information in a more concise way. That's sort of related to parsimony. So the only one that really relates to parsimony is the sort of over-identified model. You're explaining more data points, right? Covering the data points with fewer estimates. So that's sort of a way to get to parsimony, to try to simplify. So when you hear parsimony, think like simplification, or you're trying to simplify things. Let's try to find a model that makes the relationships between all these data points simpler, more parsimonious, right? So because of that, the goal often is over-identified models, because we want to try to explain as many things as we can with as few parameters as possible. All right. So what about step 2A? I'll give you a hint. All right, so both step 2A and 2B have to do with the same thing. Both have to do with the factors. That's why they're sort of together, about establishing factors in a model, the latent variables. So remember, factors don't exist. So how do we make them exist? What do we do to make them real, to make them measurable? There are 2 steps we got to do to make sure these factors actually work and can be established. Nobody remembers? Nothing? So if they don't exist, how do we measure them? How do we use them? If they're fake, right? They're latent. We can't measure them directly, so we have to be able to quantify them in some way. So how do we quantify them? There's 2 ways. That's still part of step 2A. There are 2 ways in which to quantify latent variables. That's just the sort of labeling of them. That's not, the endogenous, exogenous is sort of how they relate to one another. But in terms of making them exist, like, right? So these are variables that don't exist. So how do I take a latent variable and predict another latent variable with it if they don't exist and they don't have a numeric scale to them, right? They have no scale. We have to be able to give it to them. And we can either do that, go ahead. Okay, so we use the indicators. So we give them, we use their the measured variables to sort of indicate a factor. But even then, the factor doesn't necessarily have a scale. So we have to figure out a way to give it one. We can either do so in an artificial way, or we can do one a little more concretely. So the sort of artificial way is just to assign, so step 2A, I'll just say, is to sort of give any factors scales, or a scale. And there's 2 ways for that. There is, I called it like there's like unit variance approach, UV, and there's a unit loading approach. So in unit variance, they're basically just assigning the variance of the factor. You're just saying it's 1. And by doing that, you're saying it's basically like a z-score. It's just an artificial sort of standardized scale that is being measured on, and we're just going to use that scale, like a z-score scale, to identify that factor. That factor is now is quantifiable or quantified by the fact it has a unit variance. Okay. Unit loading is that you pick one of the indicators. So that's when Hector said the indicators, I was like, okay, keep going. You were so close. So yeah, so you use the indicators, but you're going to choose one of the indicators, and you're going to fix the loading to 1. So it's called unit variance or unit loading, because you're assigning a unit, 1 unit, like a single value, to the variance of the factor by essentially just saying, look, here's my factor. It's going to have a variance of 1, right? Or here's my factor, and I have, let's say, a few items here. whatever this item is, item number 1, I'm just going to assign that one a 1, and then I'm going to estimate these other ones. Right? So I'm going to take one of the loadings and assign it a 1. Or I'm going to assign the variance of the factor 1 and make it basically a z-score scale, standardized z-score scale. Okay, make sense? So we have to be able to give it some kind of quantifiable numeric scale, and we do that by either saying it's got an artificial standardized scale, or whatever the scale of this variable is. Let's say it's on a Likert scale or something. Whatever the variance that item has, that scale is now going to be transferred over to this factor. So it has a similar scale that that item has. It's now being scored in the same way that this item is. And if all the items have the same scale, they're all like Likert scale items, then they're all going to have a similar scale to one another. It almost doesn't really matter which item you choose. In most programs, whichever item happens to be the first, like if you're using a spreadsheet like SPSS and pulling it into a program, whether it's M+ or EQS or I think even Levon and Amos and all these other programs, whatever the first one is left to right in the spreadsheet, that first one gets assigned a 1. It just chooses it. You can change it if you like, but because the downside of this method is that you don't then get an estimate of the loading for this item. Right? So these ones get estimated, but this one, it's been fixed. But now it gives the factor a scale that's similar to the item. So we now bring, this is basically like breathing life into the factor, right? The factor didn't exist. This is like the resurrection of the factor, or the, I guess not really the resurrection, it's just there's no word like surrection, just, like there's no, they're not being resurrected, they're being erected in the first place, right? So they're being brought to life, right, by either attaching it to one item so it has the same scale, or just saying, look, I don't care about the scale of the factor, I'm just going to standardize it and make it like a z-score scale. So that's the first. Go. So unit variance or unit loading. Right, so this refers to unit variance, that refers to the unit loading. I think it's sometimes called unit indicator or something like that too. But so that's cool. So now we're making the items, these factors sort of exist. We're bringing them to life, right? What's 2B? So still talking about how to make these factors exist. So we're giving it a scale now. What's the other half of it, the other part of it? We gotta give it a scale, and then there are some other rules about making sure the factors can be identified. The analogy I used for this last time was a table. Factors are like tables. In order for a table to stand, it has to have what? Okay, so you're right, but back up a second. So just think about one factor by itself. So if there are no other factors, what's the minimum number of legs that table has to have? Right, which is 3. Right, so you have a minimum of 3. Maybe, and even then, that may not be the best table, right? A 3-legged table may not be the best, most stable table, but it's the minimum you need for a table to stand up is at least 3 legs. So this has to do with the sort of number of indicators for a factor. Okay, and the reason I'm just writing this is because there's a lot of scenarios. If you only have one factor, then it's got to have at least 3 items, and none of the errors or the unique variances for the items can correlate. Like all these sort of rules. If you have more than one factor, as Lauren started to state about the 2 factors with 2 legs, 2 tables with 2 legs, if you can start to get away with having less than 3 indicators if you have other factors that you can correlate them with. So if I have if I have factor 1 here, factor 2 there, and they each only have 2 indicators, I can get away with this as long as the 2 factors are correlated with one another. So it's like, think about two-legged tables. As long as they're sort of attached to each other, they can sort of hold each other up and make, one stable sort of table. But even then, this is sort of a minimum and not recommended. Right? So every once in a while, you'll see, these sort of factor models, these structured regression models, where there are, a bunch of factors, and some of them may only have 2 items. They can get away with that because there's so many other factors in the model. They're sort of holding up that one factor or a couple of factors that have only 2 indicators. But in general practice, you want at least 3 indicators at a minimum. Because you got to think about it, if you only have 2 items, these 2 items really, when you're talking about factor analyzing those 2 items, it's kind of silly because these 2 items really, this is only one correlation. So you're creating a factors based on a single correlation. Factors are meant to find patterns of correlations, right? Group correlations together. You can't group one thing together, right? It's just one correlation. So this one factor is based on a single correlation. So it's sort of it's not even really a factor in the first place. And the only reason why it's identifiable is that there are other factors to sort of help hold it up. So 2 ways, you got to give the factor scale. 2b, the number of indicators needs to, you need to meet the minimum number of indicators, which is 3 when there's only a few factors with no correlated errors. It starts to get a little bit lax as you add more factors. With more factors that are correlate, you can get away with less items. You can get away with some correlated errors. You can get away with some other things as long as there are multiple factors sort of happening at the same time. The smaller the model is, you're back to at least having 3 items to hold up a factor appropriately and make sure that it's identified. So what else? What else do we need with all this stuff? We got number of data points. It's just 0. You got to make sure we have more data than parameters to make sure it's over-identified or at least just identified. We got to give the factor scale and make sure they have enough indicators to sort of to be factorable or to be identified. What's the last part? What's the last step? In order for a model to be identified, there's one more thing it's got to have. One more thing. What's that last thing? And it's the thing that I talked about a couple times as the thing that for me I always found the most confusing, and I always mixed them up. The term always seemed backwards to me. Remember? It has to do with the flow of the model. The first letter is R. It has to do with how the model flows. How should a model flow? Like a river. I hope not. That'd be a really weird model. River? No, it's not like a river. I mean, it's in a river in the sense that, rivers flow in what direction? Like, do you see rivers? Yeah, they go in all one direction. Rivers don't flow in a circle. They don't flow backwards. They don't have part of it going forward and part of it going backward. They flow one direction. Sometimes they may split off, but they still are all going sort of one direction even as they split. So what's it called when a model goes in all one direction? It doesn't go back around on itself. There's no feedback loops. That's called recursive. So in step 3, we want to make sure that the model is recursive. Right? So if a model is recursive, It means a couple things. I mean, obviously it means it flows all in one direction. There are no feedback loops. It also means some goofy things like as the model goes forward, the exogenous variables shouldn't have related errors that correlate as well, because that actually can cause a feedback loop that way too. But you don't want a model in which the flow is sort of where something is predicting other things and then sort of somehow ends up back predicting something back in the beginning of the loop and sort of creates this sort of thing. So you want the model to sort of go all in one direction and to be free from issues like that, because if and to be free of things like this where you have a model where, let's say you have X predicting I don't know, Y and Z. You also you can say that Y also predicts Z like that, that's fine. But you can't then turn around and say that Z predicts Y. You can't do that. Right? This is really just a correlation, right? If you're trying to get a directional prediction from Y to Z at the same time you're getting Z to Y, this is what's called a feedback loop. It's called a feedback loop because as you're trying to estimate the one prediction, it's also trying to estimate the other prediction, and it's like it can't find, it's just going to keep trying to estimate it and won't ever find a solution. So like a feedback loop, it just sort of keeps going. So it should be free of those. Like you don't want these, right? This is not how you want. That's not recursive or non-recursive. All right, so those are the steps. You need to know the number of data points you have. You need to be able to figure out if you have more data than parameters, or at least the same number. You got to be able to give the factors a scale, like make them quantifiable, numeric. And you need to make sure they have enough indicators so that they actually work as factors. You can actually, they are decent factors supported by enough indicators. And then you have to make sure that the model is recursive. And if you have all these things together, then the model is identified. And then you can move on to the estimation phase, the estimation part of the process, because you have enough things established to make sure that the indicators can be identified, the loadings can be identified, the errors can be identified or estimated. I mean, any predictions you have between the factors, the correlations, all those things can be estimated because you have enough things in the model that are fixed and specified correctly, that those things that you want to estimate can be estimated. All right, so let's talk about estimation for a sec. And again, we're not going to get too much into the details on this just because I don't want to. I don't think you want to either. But so after you've specified a model and the model is identified, you've sort of met all those criteria, right? The goal of this is to try to, let me back up actually. So the thing that we're trying to do, just in general, without thinking about a whole lot of crazy equations, is that the model that we are estimating, right? We're specifying some diagram, a picture, converting those into equations. We're going to use those to estimate things, which are then going to be converted back into what's called the sigma theta matrix, right? And this is a fancy way. So sigma and S are usually used to refer to things like variance, covariance, those kind of things, right? So this is the sample. This is the thing that we, the actual data we have. This is our sample. And this thing is the model-based variance and covariance matrix. This is the sample variance covariance matrix. And this is the one based on the model. The reason why we call it sigma theta, so the theta sort of indicates that it's model-based, right? Even though that doesn't make sense now, but this is a model-based estimate, and it's a parameter, so it's a population estimate. So this is what we're hypothesizing is going on in the population. So we're making this model thinking, I think this is what's happening in the population, and I want to see if that explains what's happening in my sample variance covariance matrix. So we want to be able to take the sample covariance matrix, so tracked out the sigma theta matrix, and get a what's called a residual matrix. Right? We want to be able to, we should be able to do that. We talked a little bit about that when we talked about factor analysis, that you had a correlation matrix, you'd factor analyze it, and you figure out how many factors to keep and all those steps we did. And then it would recreate the correlation matrix, and then we could subtract the correlation matrices based on our original matrix, based on the reproduced matrix, based on the factor model. And then we would try to see, that the residuals, if it's a good model, these residuals should be small, right? It should be because if our model really explains our data, then the residuals at best should all be zero. Right? There's no residuals, nothing left. Our model explained the data perfectly well. That's not going to happen necessarily, but we want the residuals to be as small as possible. With me so far? So this is our sample. This is the model-based variance covariance matrix, and we want to try to make that as small as possible. But how do we actually test it? And so we actually want to be able to. We can just look at it and say, oh, it looks small. Looks like the numbers are all pretty small. But we actually want to be able to test to see, how well it's done. At the same time, be able to estimate what parameters go into the model to make those residuals as small as possible. So let me say that again. I have a model that I've sort of drawn out. I've specified it into equations. And what the estimation process is doing, it's saying, all right, I have this model. I have this sample-based covariance matrix, and my goal is to try to make that difference as small as possible. So what the estimation process does, the reason why it's complicated, we're not going to be going too much into the details of that, is because it's trying to find estimates for things like loadings, covariances, variances, the regression coefficients. It's trying to find those estimates that make the difference between our sample and our model as small as possible. Right? So in the background, the computer's like, all right, what number could I put here that's going to make the residuals small when I subtract the S and the sigma theta matrix from each other? Right, so the goal is to try to make that as small as possible. The way that gets sort of illustrated is in this thing here, this Q. So Q is the difference between S and sigma theta, and S and sigma theta is here again, and then there's a W matrix in the middle. So this is the difference between the sample and model-based matrices twice with a W matrix, where W is it's just called a weight matrix. This is W for weight. How are we weighting that difference? So the population parameters are estimated with the goal of minimizing this difference. So in the background, we're trying to figure out what estimates, what model parameters can go into the model to make the difference, this Q, as small as possible. Why is S and minus sigma theta here twice? Well, the weight is sort of in between them, but imagine the weight wasn't there. Take the W away from there again. So why is it there twice? Because what kinds of differences are we usually trying to minimize? And think about a regression equation. What are we trying to minimize? Try to make as small as possible to know that our line fits. Do we typically use just plain differences? We just subtract and we look at those. So we want to minimize error, but to do that, we can't just subtract things and get errors. The reason why is because just about any line, speaking of regression now, any line going through the points will probably do about as good a job, and all the residuals are going to sum up to zero, because you're going to have positives and negatives all going to sum up to zero. So how do we typically look at errors? If we want to know if we've made the errors as small as possible, we usually do something to them first before adding them up. We talk about regression. Regression usually is referred to as a least squares regression. Right? We're trying to minimize what? The squared differences between the predicted points and the actual points. So it's not just the difference, it's the square difference, right? So when we look at errors, we take all the errors, we square them, sum them up, we get an error variance. This thing's doing the exact same thing. It's taking the difference between the two matrices, and it's transposing it, transposed, right? Times itself. So this is just looking at, this is just a fancy way of saying I want the squared difference between those two matrices. S minus sigma theta times itself is just taking the square difference, but it's because they're matrices, I can't just square them. I have to multiply them by their transpose to make sure that they actually can, that the matrix, as a matrix, is being squared, not just the values. Okay, so this is just a fancy way of saying I want the square difference between the matrices, right, those two sides, and then I'm choosing a weight matrix. The weight matrix has to do with just how do we want to weight the variances? Where do we want to put the importance? Is the importance more about the variances and more on the covariances? How do we actually want to weight the difference between these two things when looking at this squared difference? And the choice could be that we don't want to weight them. It could be that I'm not going to weight them at all, right? We could just not do that. But typically we're choosing some form of weight matrix when we're looking at the differences between these matrices and then taking that squared difference. Okay, so in factor analysis, we compare the covariance matrix, actually the correlation matrix, and the reproduced correlation matrix to look at fit. In SEM, this is extended into an actual test. So when we actually find Q, that minimized value that we just talked about, and I multiply that by n minus 1, this is the number of subjects, number of responses minus 1, it actually converts the Q into a chi-square. We actually get a chi-square distributed value, and then we can actually look it up and see if it's significant. So in this case, significance, and we'll talk more about this again, but significance in this case is bad. So if I take n minus 1 times q, remember that the idea is I want to make this thing as small as possible. If I take q times this thing and it ends up being significant, that means that my S and my sigma theta matrices are significantly different. That's not good. So in terms of fit, we actually want this chi-square value to be not significant. We want it to be as small as possible, because that indicates that the S and sigma theta matrices are actually similar, that they're close enough together to not be significantly different. So the difficult part, and it's not that difficult in terms of you're more than likely going to use the same one, the sort of default estimation method. The trick, though, does come up when you have to deviate away from the default and choose other methods. It can be kind of tricky in figuring out what that is. So how do we choose that W matrix? Because how we weight the difference may have an impact on exactly how it fits. So there's a bunch of different ones. There's lots of different estimation procedures, and they all differ in terms of the weight matrix. It's the same process for the most part, but they use a different weight matrix. So ULS is sort of obvious. It's unweighted least squares, so it literally doesn't use a W matrix. I mean, it does, but it's the identity matrix, so it just basically doesn't weight anything. You have generalized least squares, which goes back, similar to least squares regression. It's more generalized least squares. Maximum likelihood. There's these other crazy sounding ones: the elliptical distribution free and the asymptotically distribution free, which are supposed to be almost like non-parametric equivalents, where we're trying to estimate this process without assuming normal distribution and all those kind of things. And then there are this Sator-Bentler, or sometimes they're called the scale or robust chi-square methods. It's basically a maximum likelihood estimate that they actually then correct it to help whenever you have non-normal data. Okay, so again, you don't need to, this is not something you need to memorize or need to know like the specifics of these, but this just goes through like unweighted least squares. You have that difference between the two of those. So this is just writing sigma as a capital, but S minus sigma theta squared, okay? but where W is the identity matrix. It's basically just all ones. That's why it's called unweighted, because there's no weights. It's not weighting anything. Generalize these squares, it really is just weighting. That W matrix ends up being just the, it just says any consistent estimator of sigma. So oftentimes we just use S. So that literally it's taking S minus sigma theta times itself, and we're dividing, because it's W, the weight matrix is the inverse of it. It's the inverse of the same S matrix again. For maximum likelihood, you can tell it gets a little crazy, because now instead of just taking the difference, we're taking the logs of those things and getting a difference of the logs of those, which is, it's the same idea though, so taking a difference and squaring it, where again, instead of taking the S matrix, we're taking the sigma theta matrix and using that as what we're inverting, what we're actually dividing by, what the weight matrix is. It's the inversion of the sigma theta matrix. These get just nuts trying to even understand what's going on, because they get a lot longer. So what these both do, by the way, is things that affect these models are things like skewness and kurtosis. So it actually estimates skewness and kurtosis, and there are different measures of kurtosis, and actually tries to control, to adjust for those in both these different methods. But again, it's W is any consistent estimator of sigma. K and I believe that's delta are measures of kurtosis. W in this one is this nuts thing down here, where it has, again, it's the looking at the kurtosis of the values, the things that actually make it sort of non-normal, and it's sort of it tries to adjust them out so that the distribution doesn't have the impact on it that it would in these other ones. So what's the point of showing you this? The idea is that it's the same process, the same principle applies to everything that we're doing. We're trying to find a model that best explains our data. And so we're specifying this model the way we think it actually works. In the background, right, though that model is getting translated into equations, and then the program is going to estimate those parameters to make the difference between the S and sigma theta as small as possible. Now, the only trick to that, the only thing that makes it complicated, is as it's doing that, it's actually it's choosing these different weight matrices. For the most part, maximum likelihood is the default typically in most of these programs, whether it's, again, Levon, EQS, M+, like the default is typically maximum likelihood. So this is the one that's going to be used most often, where we're going to basically be weighting it by the size of our model-based covariance matrix. The details, again, don't necessarily matter. What does matter is the process. We're trying to estimate a model. The program is going to try to find estimates that best make the difference between our model and the data as small as possible. And it's going to iterate through those. It's going to do, these are almost always, I think, except for maybe unweighted, it's going to sort of iterate through to try to find the best solution. The one we typically use is maximum likelihood. It's actually trying to maximize the likelihood of those estimates in the model to make the difference, that residual, sort of as small as possible. That's sort of the goal of all this stuff. Okay? Again, we're not going to go too much. This is about as far really into the details of estimation that we're going to go, really, as you know. I'm not going to go into the expectation maximization algorithm of maximum likelihood. I'm not just, I don't know if this is not the goal of this class. To me, it's more about getting you to use these models and translate them into hypotheses and stuff like that. Not going too much into the mathematics. All right, questions, estimation. The one thing that I do want you to understand is what are the components that are in this, oops, wrong direction, that are in that Q. So what is going on in Q? All right, so Q is really just the squared difference between our data and model-based covariance matrices squared times some kind of weight matrix. So understanding the pieces of this without really getting into details of, well, what weight matrix goes with what kind of estimation procedure. I don't really care about that so much. I just want you to understand what's going on. Because this really gets back to the goal. What are we trying to do? We're trying to find a model that is the closest to our data, and we can make this as small as possible. All right? That's the goal.